Okay, hello everyone. So I have shared the lecture slides and I hope you guys can see my screen. So in last lecture we were talking about thread synchronization, right? And we said that we if you don't want uh if we want our program or our code to be thread safe, so we don't want to end up in a race condition. So race condition mean like we don't want to end up in a situation where if we run the program multiple time and we end up seeing different results, right? So and the reason for that behavior is when the data which is shared among multiple threads, the access to that shared data is not synchronized. So how we can make our code thread safe by protecting the shared data by putting some locks. So which mean like any thread which want to access the shared data, it first need to acquire the lock, and then once it is done with accessing the data, it needs to release the lock. And here the basic assumption is that only one thread can get the lock at a given time. So it is not allowed for multiple threads to get the lock at the same time, right? Otherwise, there is no point of doing the synchronization, right? And then we had an example of naive implementation of locks, where we just wrote two functions, lock and unlock, and then we had a look at their assembly version, and we found that like that naive implementation is not correct, and the reason for that naive implementation to be not correct was that we were accessing that lock variable in one instruction. We were reading it from the memory, then we were testing its value, and then we were setting its value. So we were doing three different operations in three different instructions, right? But as a result, what can happen is like if one thread has read the value and tested it, but before it sets the value, another thread can come, read the value, test the value, and set it. And when the thread A comes back, it will see that it will also set the value and assume that it has received the lock. So what will happen that two threads have the same lock at the same time, which is not what we want, right? So the basic problem is that the operation of reading the value, lock value, testing it, and setting it is not atomic. These are three different instructions. So we need some instruction which can perform all three operations in a single instruction. Or in other words, we need an atomic instruction, right? So we are not going to, at this point, we are not going to look at the atomic instructions because uh, yes, there are some instructions, for example, compare and swap instruction, which maybe we will be using in one of our projects. So when I will give you the project description, I will mention it there, and I will give you the hint about, for example, how you can search for it and how you can use it. But uh, atomic instructions, they are enabled by the underlying hardware, right? So we need hardware support available so that atomic instructions can work. So atomic instruction is one which can test the value, which can read the value, test the value, and set the value in a single step, right? So in this setup slide, we are first going to look at another solution of implementing the lock. It is again software-based solution. So it doesn't rely on atomic instructions, but it will still work. Uh, and it will actually, it doesn't have the same problem as our naive implementation of the locks in previous lectures. So which basically means that it does not allow more than one thread to access the global data or shared data at any given time. So it means that if we use this implementation of locking, only one thread can get a lock at any time. Okay, so let me walk you through this, and then we will see what are like good features or what are the downsides of this approach. So this algorithm is basically known as Peterson algorithm. And okay, let me first select the pointer. So this is known as Peterson algorithm for mutual exclusion. So mutual exclusion, what is mutual exclusion? Mutual exclusion is that when two or more threads, they want to access the same shared data, So the mutual exclusion is the property that where only one thread can access that shared data at any given time. So if thread 1 is accessing the shared data, no other thread can access it, right? If thread 2 is accessing, no other thread can access the shared data at that time. So that is known as mutual exclusion, right? So here again, we are implementing lock and unlock functions, but now in a different way. So here first we have global variable, two global items. One is the variable turn and the other is interested, right? So interested is like if we have two threads, so we will have an array with the name of interested, but it will have only two elements, right? So in by like for example, if thread one is interested in getting the lock, so first you need to just advertise your interest. So you need to first show your interest that I am interested in getting the lock before actually getting the lock, right? So if thread zero is interested, it will set the zeroth element of this array equal to one. If thread one is interested, it will set uh, element one of this array equal to one. Okay. Now let's have a look how this lock and unlock function works. Again, remember, you first any thread first need to call the lock before accessing the global data or the shared data, and then it needs to release the lock after done with accessing the shared data. So this is how the lock function is working. So here the process is the ID of the process or ID of the thread which is calling it. Here in this slide we are using the terminology of process or thread interchangeably. You can say we are considering a single threaded process. So if there is a single threaded process, mean there is a single thread, right? So we can use the word of process or thread, doesn't matter. So here like process is actually the ID of the process, like it can be 0 or 1, right? It is not the ID which is given by the operating system, but a user given ID, right? So which can have the value of 0 or 1, right? And here we are assuming in this example that there are only two threads involved, right? So here you are giving int process, and then int other is 1 minus process. So if for example if process is 1, other will become 0, right? But if process ID is 0, other will become 1, right? So then uh, this process then the process will actually advertise its interest by setting its element in the interested array equal to true and setting turn equal to other. So here basically we are saying that wait if the other if it is if the other process is interested and it is the turn of the other process, right? So here we are saying like uh, so just let's assume that okay, maybe I need to go to the okay. Let's start with this slide because it is more like kind of clear how things are working here, right? Assume like we have interested array initially set equal to false. Interested 0 is equal to interested 1 is equal to interested false, right? Is equal to false. So it is false. All the elements are initialized to false, right? On the left we have thread 0, on the right we have thread 1. Let's say that both threads starts executing at the same time and both invoke the lock, right? Both try to get the lock at the same time. So for process thread 0, process is equal to 0, ID is equal to 0, right? And for thread 1, the ID is equal to 1, right? For thread 0, other will be equal to 1, but for thread 1, other will be equal to 0, right? Now, thread 0 is setting interested of zeroth element of interested equal to true, and thread 1 is setting interested element 1 of interested is equal to true. Both are actually advertising their interest, right? And here turn will the turn is equal to other, and thread 1 is saying turn is equal to other. So what is happening here? Actually, both thread 0 and thread 1 both want to write the value of the same memory location or the same variable, which is turn, right? Now it is not possible for two threads to update the same memory location at the same time, right? So which means that there will be a conflict. So what will happen that memory controller or the system, it will allow one of those thread to succeed, like one of those threads which are requesting, one of them will need to wait and the other will go ahead, right? Now we don't know which one, as a user, we don't know which one will go ahead, right? It is the decision of like memory controller, which is not part of this course, but because it is a hardware component, right? So one of these thread will be allowed to go ahead and write the value of 10, right? Now let's say that thread 0 or process 0 is allowed to write and thread 1 is made to wait, right? So if that is the case, then turn will be set equal to 1 by thread 0 here, right? And if uh, and then let's say that after that thread 1 updates that turn value of variable turn, so it sets turn equal to 0, right? Thread 1 writes after thread 0, resetting the value of turn to 0, right? Everyone is with me until this point? If not, let me know.
So how does turn equal other work with thread 0?
Yeah, so do this math here. Do you get it? No.
So other so
So
other
what is other?
is
And 1 minus process, right?
mhm, yeah.
And what is the value of process in context of thread 0? It is the ID of the thread, right? So 1 minus
Mhm,
0 is equal to 1. So other is equal to 1, right?
yeah.
And here the process is equal to 1. So 1 minus 1 is 0, right?
Mhm.
Yeah. Okay.
So isn't turn always going to be equal to other?
Yeah.
Because or for the while loop, because turn equals
What do you
other
mean by it?
of
Isn't that going to be always equal to? Yes, it will be always equal to other, but the value of the other will be different in context of thread 0 and thread 1. In context of thread 0, other will be equal to 1, but in context of thread 1, other will be equal to 0.
It's because we initiate other as 1 minus process value. That's why 1 minus 0 is still 1, whereas 1 minus 1 is 0. And thus, no, wait a minute.
Hmm. Then how does other change? So that it'll let thread 1 go after thread 0.
No, I see what you mean. Yeah, because turn equals other after other has changed, so turn will always equal other. Yes?
Uh, it's pretty straightforward. Okay, let me try to explain again. Okay, let me get rid of all these annotations and start from the same slide. Let me again get the marker. So, are you with me until this point? On thread 0, process is equal to 0 because that is the ID. Process is nothing but the ID of the thread. In thread 0, the ID is equal to 0, right?
That makes sense.
And in thread 1, the ID is equal to 1, right? So
Yes.
process is equal to 1. Everyone with me until this point, right? So
Hmm.
in thread 0, what will be the value of other? 1 minus ID, which is 0. 1 minus 0 is 1,
Hmm.
right?
Yes.
So other is equal to 1. Both are, so if you are like getting confused, so assume like this. You have two cores. You have two cores. I don't want to write the spelling of the code, but just understand that. These are two cores, right? And thread 0 is running here, and thread 1 is running on this core, right? So they are running at the same time on two different cores. Okay. So that's why, and these like this other and this other, these are their local variables,
Hmm.
right?
Yeah.
Okay. So, okay. I want to make it clear, but then the problem is that when I do like how to say, when I explain it more, it takes more time, and then we are falling behind already from our syllabus. Okay, let me go back to OneNote then. week 8, day 2, right? And let me, okay, I cannot put them side by side, but yeah,
That's fine.
just try to, yeah, try to follow me here. So, okay. So here I'm writing thread 0, here I'm writing thread 1, right? And remember, turn is global variable. Turn is, sorry, turn is a global variable, and interested is also global variable, a global array, right? Which means that both thread 0 and thread 1 can access them, can view them, right? Now in thread 0, the ID is, I'm writing process, right? Process is equal to 0. Thread 1, process is equal to 1, right? Now let's say both are running on core A, thread 0 is running, on core B, thread 1 is running, right? And let's say both start execution at the same time, right? So for thread 0, other becomes equal to 1, right? And for thread 1, other becomes equal to 0. So we are at this point for both of them, right? And let's say then both of them move to the next thread in execution, or next instruction, right? So it sets interested process equal to true, right? Remember, interested is an array. Again, this is a global array, 0, 1. So thread 1 sets this equal to 1, and thread 1 sets element at index 1 equal to true, right? Now, then, though both want to write the variable turn, right? This variable. But this is a single memory location. How is it possible for two persons or two threads to write the same memory location at the same time? It is not possible, right? So what will happen? That one of them will be given the access and other will be asked to wait. Let's say that thread 0 is asked to given the access and thread 1 is asked to wait, right? So if thread 1 given the access, it will set turn equal to other. What is turn in its context? 1. So it will set turn equal to 1. And let's say once thread 1 is done with writing, then thread 0 is done with writing, then thread 1 is allowed to write. So it will overwrite the value of turn, right? With its own value of other. What is its value of other? 0, right? So it becomes 0.
Okay.
Final value of turn becomes equal to 0, right? Is everyone with me until this point?
All right, I see what I missed. I didn't think about the fact that the other one would pause and the other one would then update the value of turn or other.
Yeah, because remember I said the memory controller will allow only one writer to write a given memory location at a given time. Okay, now I can go back here, right? So the final value of turn is equal to 0, right? Now let's say after that both of them execute the while condition, right? Let's look at them one by one. Actually, both of them, because they are running in two different cores, so they execute at the same time. But being a human, we cannot like look at and try to understand both of them at the same time. So let's first have a look at thread 0. So what will happen at thread 0? So it will execute this while condition. So it is saying interested other. What is other in this context? Remember, it is the value of turn is equal to set equal to 0 now, right? Value of set final value of turn is equal to 0. So it is saying interested 0 is the so here there is a mistake. So interested 0. If the other one is interested, yes, it was interested, right? I told you, I show you on the note that the interested is set equal to 1 for both elements, right? And turn is equal to other. So no, sorry, my mistake. Here, this other is the local variable, right? This one. What was the value of other? 1. So here it is 1. So interested 1 is equal to true? Yes. Now let's look at the second part of this condition. Turn is equal to other. So is turn equal to other? What is other in the context of this thread? 1. So turn is equal to 0. So it's mean it is not equal to other. So condition is false, right? So if condition is false, what will happen? That this this if the
The
condition
while
is
loop will
false,
stop
then we will
waiting.
not enter the body of the while loop, right? Right?
Yeah, so if you don't enter that, then it'll stop
Body
waiting.
of the while loop. If you don't enter the body of the while loop, then it's mean you go through the to the next line here after the curly braces, right?
Mhm.
So it's mean you are not waiting. Thread 0 is not waiting, right?
So it being locked is just it waiting.
Sorry,
So it being locked is just it waiting.
say it
Or
again.
so when a thread is locked, is that it being waiting or not waiting?
Yeah, so when the thread gets the lock, it doesn't wait. When it fails to get the lock, it keeps waiting. So here what we are saying is that thread 0 is successful in getting the lock, but thread 1 is not able to get the lock. How? Let me explain by explaining this while loop. Did you see that in case of thread 0, the while condition was not true? So as a result, we didn't enter the infinite loop and we moved to the end of the curly braces or curly end of the block. Now let's see what happens in case of thread 1, right? So in case of thread 1, what is the value of other? The value of other is 0, right? What is the value of 0th element of the interested array? It is true. Okay, so first part of condition is true, but it is an and, right? So what about the other part? Turn is equal to other. So what is other? In this
0.
case, it is equal to 0. And here turn is equal to 0, right? Remember, the final value of turn was 0 and other is also 0. So condition is true. So if the condition is true, what will happen? We will be in this infinite while loop, right?
So it starts waiting.
Yeah, so it starts waiting because it cannot continue. Basically, the main idea of Peterson's algorithm is that every thread allows first ask the other thread to go ahead. It gives the chance to the other thread to go ahead if it can, right? So for example, here it was saying if turn is equal to other. If it is not my turn, if it is the turn of the other thread, then go ahead. Yes, the turn was 0. So turn was equal to the other thread, not my turn. So that's why it starts waiting, right? And here it was checking if turn is not my if it is not my turn but the turn of the other thread. What is the other thread? 1. But it was not the turn of the other thread. Why? Because turn was equal to 0. Where? Here, right? So the main idea is like for it is like at an abstract level, it is like this. You and me, we both want to read the same book, right?
Mhm.
I I advertise my interest by writing on the board that I am interested, and you also advertise your interest by writing on the board that I am also interested. But we both are like, trying to be kind to each other. And I say, okay, if it is your turn, then go ahead. And you tell me that if it is your turn, then you go ahead first. For that, we need to first check whose turn it is. So if it is my turn, I will go ahead. If it is your, you will go ahead, right? And the main point is that only turn is a global variable. So only one thread can write it at a given time. So it has one single value, right?
Yeah.
So you were saying like turn is equal to Naveed, and I was saying turn is equal to student, right? So, but
Mhm.
I mean, I was the one who wrote it first. I said turn is equal to student, but you are more kind and you came and said, no, our writing turn is equal to professor. Okay. So when that comes, what happens is like here, what happens? Turn is equal to professor, right? So if turn is equal to professor, now you are waiting and I go through.
But then how does thread's turn change?
Yeah, okay. For that, we need to, for that. So, for example, now, let's say thread 0 has received the lock, right? The professor has received the lock. Now, what will happen is that I need to release the lock for that. Okay. So, for that, let me show you where is the unlocking part here. So, for unlocking part, once I'm done with critical section mean once I'm done with accessing the shared resource, for example, let's say reading the book, I will say interested process equal. I will say I am not interested anymore, right? So when
I
I
see.
will say I am not interested anymore, remember you as a student are waiting here in this loop, right?
So then that one will
So if
stop waiting.
I say I'm just not interested anymore, so here it will be interested professor. So this will become false, right? Because I said I am not interested anymore. So when this will become false, you will go through.
Okay, I understand.
Okay. Any questions? I know it is a bit tricky. It is a bit tricky. That's why I try to do like this kind of animation where you can see how things are progressing. But you need to do the timing of these two different threads on your own using this Peterson algorithm to like so that you can internalize or understand how the algorithm is working. Okay. Any questions? Okay. So this algorithm, it doesn't need any atomic instructions. Atomic instruction mean, remember we said an instruction that can test the value of the condition, that can read the value of the condition, test it and set it at the same time. So it even if we are not going to cover atomic instructions in this course, but even if your hardware doesn't support the atomic instructions, still this algorithm can work to achieve the mutual exclusion between two threads, right? But but the problem is like you need to if I take you to to the previous slide, what is n? N is number of threads which are like which are sharing the same data or critical section, right? So if the number of thread is 2, we will have two elements in the array, right? But if let's say a number of threads which are interested, they are 10, it will be that this Peterson algorithm will not work as it is, right? We need to modify it. So basically this for the current variant, which we have discussed here, it works only for the case when you are trying to achieve the mutual exclusion or when you are trying to achieve the synchronization only between two threads. If you want to achieve the synchronization between more than two threads, then the current version of the Peterson algorithm will not work and you need to modify it, right? And that is known as a gating algorithm or filter algorithm. We are not going to discuss it here. Okay. So that is the problem uh, with the Peterson algorithm. And even if you modify it, then the thing is like, yes, it will work for more than two threads, but the overhead of that algorithm will become significant. Why? Because you need to test every time. Like let's say in this case, for example, I am testing, is the student interested in reading the book? If yes, I want to be kind and I will say, okay, go ahead. But assume like instead of one student, I have 20 students and all of them are interested in reading the book and all of them advertised on the board by writing that yes, we are interested, right? So I want to be kind and give the turn to all of those 20 students, and once all of them are done, then I get the it is my turn to read the book, right? So which mean that my algorithm need to check one by one, like is there anyone else who is interested? If yes, I will give the return to that thread of that person, right? So what is wrong with Peterson algorithm? That it considers n threads using the algorithm from mutual. So the hint is like if you consider n threads which want to achieve the mutual exclusion, so it will have a huge overhead. The algorithm in the current form is designed for two threads only. It can be modified to support more than two threads, but its overhead will increase significantly with number of threads, which mean that filter algorithm has poor scalability. Poor scalability mean that as you will increase the number of threads more and more, let's say from 2 to 4, 4 to 8, 8 to 16, your performance will decrease. Performance will decrease mean that it will take more and more time for algorithm to work. The latency of the algorithm will increase. Any questions? No? Okay, if no, then uh, yeah, let me see if we can do the. Okay, I'm launching this poll. Yeah, you have 1 minute to answer this one. Okay, I guess 30 minutes are enough. Many students have answered. No, 30 seconds. Okay, let me wait for some more seconds. Okay, so the correct choice is the last one, right? The overhead of locking. Okay, now let's go to the, so with that, we end our topic about thread synchronization, right? And we move to the next topic, which is CPU scheduling. So let's first talk about the basic concept and let's have a look at a motivating example. Let's say you have two processes. Let's say you have a single process, process A. So when you look at the execution timeline of that process, like when you look at what that process is doing during its execution, so it will be doing like some computation where we are saying that process A is executing and then it will start waiting. Why it will start waiting? Maybe it need to do some IO. For example, let's say it wants to read from a file, or maybe it wants to it's end up it makes a system call and it is waiting for that system call to be completed, or maybe it wants to access the page table. What is page table? We will talk about it down the line in our course somewhere, but not at this point. So basically we are saying that our process A starts waiting for an event to be completed, and until that event is completed, process A cannot continue its execution. So it is doing nothing. It is simply waiting for that event completion, right? Once that event is completed, process A again starts executing, and then maybe it will again wait for some another event. So this is like a typical, structure or typical execution timeline line of a process. A process will do some execution, then it will wait for some IO or for some system call or file handling or for some event to complete. And once that is completed, will again start doing the computation and again will end up like waiting for another event and so on, right? So when the process A is waiting, it's mean that it is yes occupying the CPU, but it is not doing any useful work. It is just wasting the time, right? Now, the duration where the process is doing some computation, it is known as CPU burst. And when it is waiting for some event to complete, it is known as IO burst, right? So actually, the execution of a process is a combination of CPU bursts and IO bursts. Now let's say we have another process, process B, which also has a similar uh, pattern, where it has an also interleaving of CPU burst and IO burst. Sometime it is doing computation and then again waiting for some event to complete and so on, right? So these two process, and let's what we are assuming is like uh, when these two processes, let's say they are running on two different cores. So if they are two running on two different cores, both of those cores are wasted in this time period, right? Here, because both processes are waiting for some IO to be completed. And again, both cores are wasted in this time uh, period, right? So we are occupying two cores, but we are not fully utilizing them because we are wasting them when processes are doing an IO. So how can we keep the CPU busy all the time? Which basically mean that how can we utilize a core in more efficient way? For example, if we can say that, okay, we will not run the both processes on two different cores, but we will run on a single core, but in such a way that we will interleave their execution of the processes. So for example, one process A is executing, so it is not it is the CPU burst of the process A, which we will allow process A to run on the core. But when it is waiting for some IO to be completed, so instead of like wasting the core, we will allow process B to run on the same core, right? And when process B starts waiting for some an event to be completed, for some IO to be completed, then we will ask process A to go ahead. And but then again, here our assumption is that by that time our process A is already done with the IO. It is not waiting anymore for that event. The event is completed for the process A, right? And then that only that we can say, okay, now process A can start executing here. And when process A again starts waiting for the event, some IO completion, and we assume that process B is done with the with its IO operation, so we can allow now process B to run again. So in this way, we are not wasting the CPU core because we are keeping the CPU busy or the core busy all the time, right? Any questions?
Is there a way to have like process A have a priority over process B?
Yes, yes. We will talk about that later on because that is part of the priority-based scheduling. But here we are trying to keep things simple because we are just trying to explain what is the motivation behind even doing the CPU scheduling, why we want to do that. But yes, you are right. There are situations where we assign priorities to the processes. Okay, so what is the schedule for what is scheduled for execution on CPU? Do we schedule a thread or a process for execution on CPU? And let's say if you say thread, so what type of thread? User level thread or kernel level thread? Or if you say process, what type of process? User level process or kernel level process? So basically the question is that to whom we allocate a CPU core. Do we allocate a CPU core to a process or a thread? And then let's say if you choose thread or process, is it user level thread or process or kernel level thread or process, right? So this takes us to our next poll. Uh, I think, yeah, yeah. Okay, go ahead and try to answer this quiz. You have 30 seconds. Okay, I can give you 1 minute. Let's wait for 1 minute. Okay, yeah. So let's have a look at the answer. So this it is thread thread, not a process, which is scheduled for execution on the core. Why? Remember, because thread is considered the basic unit of core utilization. A kernel or a operating system, it works or it schedules the execution in terms of threads, right? Because if you say, okay, process is scheduled, then there can be situation where we have multi-threaded processes, right? Now, if you say, let's say I have a process A and it has 10 different threads. So, and if you are saying that process is scheduled for execution, then which thread of that process, right? So that's why the scheduling is always at the level of thread, not at level of processes, right? And okay, so if it is a thread, which type of thread is scheduled for execution, user level or kernel level? It is kernel level. Why? Because user level threads, they are not visible to kernel anyway. And a user level thread, it must be mapped to a kernel level thread. Remember, we discussed about it in our previous topic, right? Because and the other thing is that why we do the scheduling for kernel level thread, because uh, all the resource allocation, it is done to kernel level thread. It is not done to user level thread. Kernel doesn't see the user level threads. Okay. You can ask the question like, okay, if scheduling is done at level of threads, then why we have the name of this topic as CPU scheduling? Uh, because uh, in the older times, there were only single threaded processes. So at that time, uh, whether you say a CPU process scheduling, process scheduling, a thread scheduling, it is same. So that's why people normally use the word of process scheduling. And why CPU scheduling? Because in older time you had single core processes, single core CPUs. So it doesn't matter whether you say CPU scheduling, because one thread runs on one core, right? But in older times you had only one core in your system, right? So you can say, okay, then the core and CPU, they become synonym to each other. So that's why we can say CPU scheduling. So these are some terminologies which are retained from history, but they are not like 100% correct in the sense that we schedule thread and we don't schedule processes. But in literature, you will see at many different places these terms are used interchangeably: process scheduling, a thread scheduling, a CPU scheduling. Okay. Uh, Let me check the time. Yeah, we have time yet. Okay, CPU scheduling. Scheduler is a module which is responsible for selecting one of the ready processes from ready queue to execute. Right? Remember when we were talking about different states of a process, we said that a process can be in a ready state, it can be in a waiting state, it can be uh, a terminated state, right? So and it can be in running state, right? So only threads which are in ready state, only they can move to the running state, right? But at a given time, you can have more than one threads or processes. Again, remember I said we will be using the word thread and processes interchangeably, but actually in reality, these are threads. So at any given time, there can be more than one threads which are in ready state. But let's say if you have only a single core, which one of those ready threads will be selected for execution on the core, assuming you have a single core? So that is the job of the scheduler. It is the job of the scheduler to decide which one of them will be picked. Yes, but on base of what criteria? What will be the selection criteria for the scheduler to pick one of those ready threads? So it depends upon the selection algorithm. So which means that the selection criteria, it can change from one scheduling algorithm to the other scheduling algorithm. We will have a look at a couple of them, right? Also, if a thread is scheduled or it is selected for running on a CPU, then how long it can keep the CPU? There are two options. One is that the scheduled process or thread, it can voluntarily release the CPU, that is when it is terminated or waiting for an IO. Remember, we said that during the execution, a thread or a process, it will have different like interleaving or mixing of CPU burst and IO burst. So when it is done with the CPU burst and done with computation and now start to waiting, it can voluntarily release the core or the CPU, right? Or when it is done completely with its execution and it is time for the thread to terminate itself, at that time point it can release the CPU voluntarily, right? So if this is our answer to the question that how long a scheduled process can keep the CPU, if this is the only way when a thread will release the CPU, then this policy is easy to implement because we once only allocate CPU to a thread and then wait for it to voluntarily release it. We don't need to do anything else, right? However, the problem is that it reduces the responsiveness. Why? Because let's say if you allocate a core, a CPU to a thread, and then now if you wait for it to voluntarily release the core, maybe it never need to make an IO and its execution takes long time. So all other threads, they will be waiting for their turn. So now it depends upon how long this thread which is running, how long will it take. So longer it takes, the longer other threads have to wait, and as a result, we see reduction in responsiveness from the perspective of other threads. And this is known as non-preemptive scheduling. Why non-preemptive? Because we say if the thread is running on a core, we will not interrupt it, we will not preempt it until it voluntarily releases the CPU. Doesn't matter how long it takes for it to voluntarily release the CPU, right? The other option is other possible answer to the question that how long a scheduled thread can keep the CPU is that the scheduled thread is forced to release the CPU based on a condition. For example, each thread is allocated a time budget, and when the time budget is expired, the thread is forced to release the CPU. Or, for example, if thread A is running and a higher priority thread, let's say thread B becomes ready, then we say that okay, thread B will preempt the thread A, right? So here we are saying that thread is not voluntarily releasing the CPU, right? So this approach, it increases the responsiveness and this is known as preemptive scheduling. So the main difference between non-preemptive scheduling and preemptive scheduling is that in non-preemptive scheduling, a thread will voluntarily release the CPU. But in the preemptive scheduling, a thread can be forced to release the CPU if a condition becomes true. Condition for preemption becomes true, right? However, this can create race conditions. Uh, for example, assume two processes sharing data. So let me try to explain what I meant by how preemptive scheduling can create race conditions. So let's say that we have, uh, let's say we have an array of numbers, okay? And that array has values in sorted order, right? Let's say the value is like, let's say you have A, F, I, K, right? And let's say we have two threads, thread 0 and thread 1, and they are working on this array, right? Let's say we allow, but they can access the thread only in like, they can access this array because array is shared, they can access only in critical section, which means that if thread 0 is accessing, thread 1 will not be able to access the array, right? So uh, now let's say that like thread 0 wants to insert an element, right? Insert an element where let's say it want to put an element j, right? So which means that k need to be moved towards right and then k can be written, right? So let's say thread 0 does what it performs step 1. Step 1 is it copies our k here, right? So it copies k over here, but let's say it is then interrupted. Interrupted mean like, let's say it was allocated a time unit of 1 minute, and that 1 minute after the point where it moved copied over the k is done, right? The budget expires. The budget expires, and let's say then thread one is scheduled for execution. Now let's say when thread one is scheduled for execution, and it want to access the data, it want to access this array, but when it wants to read the thread, wants to read the array, it will see the values a, f, I, k, k, right? So which is not consistent. Why it is not consistent? Because let's say we are assuming, again here I can change my assumption. One is that the array is sorted, and second, it doesn't have duplicate values, no duplicate, right? So when thread one comes here, it sees that okay, there are duplicate values, right? But why we are having this inconsistency? Because thread 0 was preempted by thread 1 before thread 0 voluntarily released the core, right? Because maybe, as we said, the time budget of thread 0 was expired, and now it was time for thread 1 to run, right? So as a result, we can have time windows where our data structures, they can be in inconsistent state. So, but then again, there are solutions for this. We will talk about them later on, but this is one problem with the preemptive scheduling of threads, that we can end up in the situation where we have data structures in inconsistent state. However, as I said, this increases the responsiveness preemptive scheduling. Why? Because we are not relying on voluntarily release of our CPU by our thread. Okay, it can also leave kernel in inconsistent state. Synchronization mechanisms, for example, locks needed to prevent inconsistency. We will talk about more about that later on. Okay, we have seen what a scheduler is, or what the job of a scheduler is, right? Its basic job is to select one of those ready threads and allow them to run on a core. There is another component in OS which is named as dispatcher, and the name of the type of job of the dispatcher module is to give the control of a core to the process that is scheduled for execution. So the job of the scheduler is to select one of those candidates from the ready threads or ready processes. But the job of the dispatcher is to actually give the control of the core to the selected thread, right? And how does it do so? By in three steps. By performing a switch context. We already have seen what is a switch context. So for example, if process 0 or thread 0 is executing, and when the context switch happen, what will the system do? It will save its PCB, it will save its states into PCB 0, and it will restore the state of the other process from its process control block PCB 1, and then P1 will start executing. So one thing that the dispatcher will do is the context switch. The other thing is that it needs to switch the user to the user mode, because the process here, P0 and P1, they both are executing in the user mode, but the in between, this job need to be done by the kernel, right? So what you need to do is that here you are in the user mode, then you switch into the kernel mode to store the state of the process 0 in PCB 0, and restore the state of the process P1 from PCB1, and then again switch into the from kernel mode to the user mode, so that you can execute the P1 process. The other thing is that you also need to jump to the proper location in the user program to restart that program. So from the perspective of the process that is switched out, you need to store the PC, and then when from the perspective of the process which is switched in, which is allowed to run, you need to set the PC to the right value where it was like interrupted. So for example, last time when P1 was moved, or it was kicked out of the core, let's say at that time point the program counter was set equal to instruction X. So now in the future, when it gets the turn again to run on the core, PC should again be set to the same address of the same instruction X. So dispatcher is responsible for doing all these three tasks. Any questions? Okay. Yeah. I think I need to put pointers in my slides about the polls. I have those polls, but you know, I don't remember where should they appear. Yeah. Yeah. Okay. Let's first go continue, and then we will have an example, and then we do the poll at that time point. So CPU scheduling, let's have a look at some Linux tools which we can use in context of scheduling, for example, to get some information. So let's assume that you have a process started with PID X. So a process is running and its ID is PID, process ID is X. So you can use this command car process and then the ID of the process and status. If you write this on the command window or the terminal of the Linux, or for example Ubuntu, then you will see the following type of output. So it will basically tell you that since the start of the process, you have like three context switches, three voluntarily context switches, and for example here zero non-voluntary context switches, right? So basically it is telling you that this process, since it has been launched, it experienced how many context switches in total and what is the type of like those switches, context switches. So it's mean that it was not preempted anytime, and it three time it like voluntarily released the core, a CPU. Another another command which you can use is VM state, or virtual memory statistic tool. And for example, if you run this tool by providing the input 1 or 3, by 1 here we mean the sampling interval of 1 second, and 3 mean number of reports. So what does it mean? It means like here, if I like when I run it on my machine, so I saw this output. So what is like how can we read this input, or what information we can get from it in terms of context switches? So here it is telling us that on average our system had experienced one context switch per second, like average across all the processes running in the machine, and 40 context switches in the last 1 second, right? And 30 context switches in the second prior to the last one, right? So it, and here by one sampling interval of 1 second mean that we want to check that how many context switches have been done after every 1 second, right? And when we say three, we are saying, okay, generate a report with three output lines, right? Now if you increase, for example, it to like vmstat 2, so what will happen that your report will be generated after every 2 seconds, and in total you will have three reports. So in this way you can actually, so these are the tools which you can see that give you information that how frequently the context switches are happening. Okay, so scheduling algorithm, uh, there are like many different scheduling algorithms available. Remember, what is the job of the scheduler? To select one of those ready threads or ready processes to run on a core. But then we should do the selection on base of one criteria. What criteria? That criteria is decided by the scheduling algorithm. Like that is the feature of a scheduling algorithm. But then if we have like multiple scheduling algorithms available, which one of them we should use to perform the scheduling, right? So it depends upon what performance parameters are critical for the application under consideration, right? And based on that, we can then select the scheduling algorithm, because uh, let's say you have two scheduling algorithms. Let's say I'm just naming A and B, and one is good at reducing the average waiting time of a process, and other is good, the algorithm B is good at reducing the average response time of the processes. Now it depends upon your need. If you are developing an interactive application, So it's mean that the response time is more important for you maybe as compared to the waiting time. So maybe you will select the algorithm B because it is better at reducing the average response time. But if you are not interested, if you are not writing an interactive application, so and you are just interested in quickly completing the your application consisting of multiple threads, right? So maybe you are more interested in reducing the average wait time of threads. So for that, you can maybe use the scheduling algorithm A. Okay. So what are different performance parameters? So we said like there are different algorithms. So if there are different algorithms, let's say A, B, C, D, and E, and you want to like compare them with each other. So for comparison purpose, or you want to evaluate them against each other. So you need some evaluation of performance parameters. So what evaluation and performance parameters are available for measuring the performance of those algorithms? So one is CPU utilization, and this is like basic motivation like, behind having a CPU scheduling, a process scheduling, a thread scheduling, right? So CPU utilization mean that how well an algorithm keeps the CPU busy, right? If an algorithm, let's say if you have an algorithm which keeps the CPU busy all the time for a given set of threads, then it's mean that that algorithm is a good candidate in context of the CPU utilization parameter. So again, if you have, it depends again, not only the algorithm, but also the type of the processes which you want to schedule. So for example, if you have, let's say you have four processes and all of them are IO bound. IO bound mean, let's say each one of those four processes spend only 10% of their time doing CPU computation and 90% of their time doing IO operations, right? So it's mean they are IO bound. So if now you are using these four processes, then they will definitely have low CPU utilization, right? Uh, so it's mean that CPU utilization is higher when you have CPU bound processes as compared to IO bound processes. The other parameter is, I think I should stop here because we are have only 1 minute left. Let me stop here. Do you have any questions? No questions? Okay, then let's stop here and today you have a quiz. So go ahead and your quiz be released, I guess, in couple of seconds or 30 seconds. I'm here until end of the lecture if you have any questions.